All right, today we're diving into something almost all of us have been through, but, very few of us actually understand: the dental X-ray. It's so much more than just a quick flash. It's a pretty amazing journey into the world of physics, and it all kicks off right there in the dentist chair.
I mean, you've been there, right? That heavy apron goes on, the technician lines up that weird cone right by your cheek and says, "Okay, hold perfectly still." But what is really going on in that split second? What's that machine actually doing, and what is it seeing? Well, that's exactly what we're going to break down.
So first things first, why even bother with these pictures? Well, think about it. Your dentist is basically a detective, but even the best detective in the world can't see through walls. And in this case, those walls are your own teeth and gums.
See, an X-ray, or a radiograph as it's officially called, is an absolutely essential diagnostic tool. It is the only way they can spot those sneaky cavities that love to form right between your teeth. It lets them see if a wisdom tooth is coming in sideways, what we call impacted. It lets them check the health of the very bone that holds your teeth in place, and find all sorts of hidden problems like infections or cysts that you'd never see with just the naked eye. Seriously, without this, dentists would pretty much be working in the dark.
Okay, so how in the world does it actually work? Well, to get that, we need to talk about the beam itself. This invisible, super high-energy force that literally travels at the speed of light.
X-rays are a form of what's called electromagnetic radiation. Now that sounds complicated, but it's the same family as visible light from a lamp or the radio waves that bring you music. The big difference is energy. X-rays are made of these tiny, powerful packets of energy called photons. And these photons are so energetic they can pass right through the soft stuff in your body, like your skin and gums.
But here's where it gets really interesting. Not all X-rays are the same. The key is something called wavelength. To get a good, clear picture, we need what's called hard radiation. These are X-rays with really short, powerful wavelengths and super high energy. They've got the punch to get through and create that image. On the flip side, you have soft radiation. These have long, kind of lazy wavelengths with low energy. And these are totally useless for taking a picture, because they just get soaked up by your skin, which just adds to your risk without any benefit at all.
So these useful, hard X-rays have some pretty wild properties when you think about it. They're invisible, obviously. They have no weight, no mass. They don't have an electrical charge, and they shoot out in perfectly straight lines at the speed of light. It's this really unique mix of features that makes them the perfect tool for peering inside the human body.
So let's zoom way in. Forget the beam for a second. Let's get down to the microscopic level. We need to understand what happens when just one of those little X-ray photons actually smacks into an atom inside your body. Because that tiny, tiny collision, that's where all the magic and all the risk really happens.
This whole process is called ionization. The X-ray photon is carrying so much energy that when it hits an atom, it can literally knock an electron clean out of its orbit. This creates something called an ion pair. You have the atom, which is now positively charged, and the electron that just got booted out, which is negative. And this is a very small but a very real biological change right at the atomic level.
So let's just walk through it one more time. A photon zips out of the machine, it travels into your cheek, and smacks right into an atom. That collision kicks an electron out of its home, creating that ion pair. Now, you need billions of these little interactions to actually make an image. But it's this fundamental process, ionization, that can cause chemical changes in living tissue. And that is exactly why safety is, and always will be, priority number one.
Okay, so you might be thinking, if these X-rays are causing atomic collisions in my body, how is this procedure so incredibly common and safe? Well, the answer is in all the layers of protection that are designed to keep your exposure as low as humanly possible. The very first line of defense is actually inside the machine itself. There's an aluminum filter sitting right in the path of the beam, and its one and only job is to block those lazy, long-wavelength X-rays, that soft radiation we talked about. This makes sure that only the useful, high-energy X-rays even get a chance to leave the machine.
Then, the beam that makes it through the filter gets shaped by a device called a collimator. The best way to think about it is like putting a precision nozzle on a hose. It narrows the beam down into a small, tight shape, making sure the radiation only goes exactly where it needs to, right onto your tooth and the sensor, and pretty much nowhere else.
And of course, there's the one we're all familiar with, that heavy lead apron. Its job is to be the final shield. Even though the beam is super focused, a tiny bit of radiation can kind of scatter. The lead apron is there to block that scattered radiation from reaching the more sensitive organs in your torso.
All of this, every single one of these safety measures, ties into the guiding philosophy of radiation safety, and it's known as the ALARA principle. It stands for as low as reasonably achievable. And what it means is that every single step, from the filter to the collimator to the apron, is all designed to use the absolute bare minimum dose of radiation needed to get a good, clear picture. Nothing more.
So let's bring it all home. We've got this safe, filtered, perfectly focused beam. It's passed through your jaw, and the result of all those atomic collisions has been recorded on a sensor. But how does that turn into the black and white image your dentist is staring at?
Well, it all comes down to density. It's that simple. Parts of your mouth that are less dense, like the soft pulp deep inside your tooth or, a spot of decay, they let more X-rays pass right through and hit the sensor. Those areas show up as dark spots. They're called radiolucent. But on the other hand, the really dense stuff, like your tooth enamel, your bone, or a metal filling, well, they block most of the X-rays. So they show up as light or white spots, which are called radio-opaque. And by reading this map of light and shadows, your dentist can uncover the hidden story of what's going on in your mouth.
So there you have it. From a high-energy photon zipping out of a machine to a tiny atomic collision in your jaw, all of it filtered and focused just right to create a map of shadows that lets us see what the eye can't. It is an incredible amount of science packed into a procedure that takes, 5 seconds? So the next time you feel that heavy apron being placed on you, maybe you'll think about that remarkable little journey.